You used to be able to buy stuff, a kit, and actually do this thing yourself, but it's a little bit cumbersome, and it's better to do it with tools and then send the board out and just have somebody make them for you. So we can start searching the details on that later, and it runs from a few $100s usually up to a few $1,000s, but we're not in the few $1,000 category here. I can tell you we're in the few hundred at the most with it, and then you kind of get your physical size you want based on the enclosure you want to put it in, stuff like that. You got to pick a connector. There's a lot of choices there, and that's kind of how you end up what you have. The power supply can give you some designs for power supplies to go with them. You get the components. The components, you can't get this Radio Shack. You'll have to go somewhere else. I got 2 places I can give you to get the parts from. But you can purchase those online with a credit card. It's not like a wholesale house you got to go to and all that stuff. It's pretty easy to come by.
So once we have our pulse oximeter and our valve, would that be when we configure all this?
Yes, you need to define those 2 things, and then you can decide what this is, and we can actually probably do some initial testing, like with the O2 sensor, and see kind of what the curve may look like or something. We may have to simulate some stuff, but anyway, do that. And the valve, we can probably do some testing with that. I can get an instrument we can set up to do pulse width on it and see if make sure the valve's going to work like we think it's going to work. So there's some things we can do before we ever go off and build anything. And I might be able to get you, let's see what your O2 sensor looks like. I can probably get you a board like this. It's got everything on it, and all you need to do is put some software on it. And that will save you a bunch of time. But it's going to be about that size. It may be a little bit larger than you would like to have, but it is certainly functional.
Yeah,
what you want to do.
This wouldn't be, we don't really have a size requirement, I guess. Okay. I mean, smaller is better, but it doesn't matter a whole lot for what we're doing.
This board cost us about $125, $130 in 1,000 pieces. And for the thing we're doing. This goes on a piece of construction equipment. It's a controller for motor speed control, engine control, and some controls on the air compressor. We actually control some solenoid valves with this, and then we send signals to the engine until it runs a certain speed, and then we got alarms on it and stuff like that. And it has serial communication. It's got RS-232 on it, and it has a CAN network, which is another form of communications on it. And see, the serial bus, I'll have to look and see if we bring. There's another serial bus on there. I'll have to look and see if we bring it out to the connector. But something like that I can get you because we've got a bunch of that stuff at the office. And then what you would do is load your software in, and you can hook that up through the serial port and download the code. I can get you some stuff to do that with. So the only thing you'd be down to just create a program.
Yeah.
To do it with.
And for our program, would we write that in C?
Yeah.
All right.
Probably the best thing to do. Basic and some of that stuff, Visual Basic and all. The language is probably, it's higher level, so the statements may be a little simpler looking than C, but they can be somewhat cumbersome in that you may not be able to get at a level and do some of the things you want to do, because this statement's done a whole bunch of things when you give it to it, and then it may be a problem. You need to look up C coding and just see what some of the stuff looks like. It's fairly straightforward. It's very logical stuff. If this, then do that sort of thing. Turn this on, turn this off, stuff like that. It's not a complex language. I think you guys can probably deal with that okay, and especially with some examples. I can give you some listings of stuff. This is what this does, and this is how it works. So I can give you a head start on a lot of that sort of thing. What else? I think that's most of it. The only other thing you get into the medical stuff, if you're going to make it into a product, which is FDA approval process you got to go through. Yeah. And that dictates a little bit about how the circuit board, some stuff's done there, and if you're going to plug it in the wall, some stuff done with the AC, things like that. So, but if you're doing a kind of a demonstration thing or whatever, you probably won't be into that realm of things. That's more on the commercial side when you're ready to go to production. But on the prototype side, not as important. It's more the functionality of it. So how are you going to simulate this thing? How are you going to take this is an optical sensor, as I remember. So how can you do something to test it with so you simulate the different levels?
Well, you're right with the pulse oximeter. We're going to get one that you just clip on your finger, and it'll read your pulse oximetry continuously real time. So I'll just come up with a set of data. It ranges from 0 to 100%. So we were just going to create some sets of data.
But can you? So you're reading off your finger. So what if your tox level's here or something and it doesn't change? So how do you make the thing change? how do you get the data to change?
By data, do you mean the pulse ox?
Yeah, the output of this device, how do you get the output, to change? Because if your levels you're reading are not changing, your O2 levels some number, what are you gonna do? Starve yourself for air or something? You know what I mean? How are you gonna make it? How are you gonna change the numbers? Or how do you simulate that so you can test this thing without having to do some human thing?
Well, like, I guess with the physiology.
Well, do you understand what I'm asking?
Yeah, kind of. Like,
If we
How
want
are we going to simulate it?
Yeah, we want to make this thing right here. We want to get an output that goes from 0 to 100%. So how are we going to do that? And maybe 0 is probably a place you don't want to be because there's a problem.
Yeah.
Usually, what you do with these sensors, there's an operational range that we call it a process range. The number's good, and then the actual sensor range is here, somewhere outside of that. But we say this is where we want to operate. The number's good in here. If we get in here or down here, we've got a problem with the sensor. We call it sensor fault, which may mean that something went wrong with the sensor and it's reading way too low or it's reading way too high. So it's broken. So we issue an alarm. In the case of this, where this board's used, most of the sensors, they go out of range. We've got to stop the machine because now it's reading bad numbers and we're trying to control and we're going to do the wrong thing. So for this guy, somewhere or another, there's a range, operating range in here that makes sense, and then anything outside of that, we've got a fault. Something's broken. You need to look at it. But what I'm wondering, how do we, unless there's some way we can, of course, we've got to find out how this thing works. I guess we need to look this thing up and see how it works. If we could simulate, we could stick something in there that we could control some variable, whatever it is we need to control. So the output of this thing varies, and then we can test everything. Kind of know how it works.
Okay.
And this right here, the other thing you can do, if this is an analog output, we can get a plain old potentiometer, put a knob on it, and with this thing and hook it to a battery, we'll get a varying voltage level depending on where it's set. We can vary the voltage wherever we want to going into here, and you'll see how the valve responds.
Okay.
So that's an easy way to test it with an analog sort of input. If this is RS-232, it gets more complicated, because now you're going to need a computer sitting out here to send a signal to the RS-232 link, to do whatever you're talking about. But I mean, that's all doable too. It's just we need to decide what pieces of the puzzle we need.
So the next step for us would probably be to get the valve and the oximeter, and then come back to this and get all the specifics.
Yeah, we need to find out. How do you? Is it OXI?
Yeah,
Yes.
yeah.
you can Google it if you want.
Pulse oximeter, OXIMETE.
I need to look that up and see.
You can use it on YouTube if you want.
Is that something that's easily to get come by and readily available? You go buy one of these things?
Yeah, you
Yes.
can order them offline. I mean, they range from like probably $20 to a few $100s.
Awesome.
But they don't all have like a way to export the data.
Okay.
Most of them are just enclosed and you clip down your finger and it'll tell you what your reading is.
Oh,
To,
okay,
like-
so it's self-contained.
Yeah.
Mhm.
Okay, all right. OX, what's the?
Meter.
Oh,
M-E-T-E-R.
I'll go Google that thing so I can find it. So this would be something like, for some of this exercise stuff you can buy, like you buy the little heart rate thing, you put on this stuff, you buy this.
Yeah, that'd be one
Something like I
possibility.
remember reading about this, and we're using those things to read your oxygen levels at different, exercise rates or something.
Yeah. The main group we're trying to affect with this would be people who are on oxygen therapy constantly. So if they're walking around, their oxygen needs are going to be greater, so they'll pick that up and then it'll change it.
Kind of like the people with the little portable tanks.
Yeah.
Exactly.
Okay, beauty. All right. And so we're talking about low flows here, probably, oxygen level.
Yeah, like anywhere from probably 2 to 8 liters per minute.
Okay, so you have to, on the valve, you got to take that into account.